Standard implementations often start and end with an API wrapper. However, deploying a production-ready system requires managing the optimization engine that sits beneath the prompt, a stack built on linear algebra, calculus, and distributed systems. Most developers interact with these models without addressing the mathematical mechanics required to make them work. They treat the system as a black box, operating entirely within the abstraction layer's boundaries. Moving beyond that abstraction requires mapping the exact path a raw physical signal takes as it is mathematically transformed, optimized, and deployed at scale. In this video, we will construct a complete end-to-end machine learning pipeline from first principles. We are mapping the specific underlying mechanics of how raw, unstructured data is converted into a machine-readable representation of intelligence. Every pipeline begins at the physical layer. We start with a raw, continuous time domain audio signal, the physical sound wave of a human voice. By itself, this raw amplitude data lacks the structure needed for machine pattern recognition. It is a sequence of air pressure changes over time, offering no discrete features for a neural network to ingest. To resolve this, we apply a Short-Time Fourier Transform, or STFT. We pass a sliding window across the time domain signal, mathematically converting it into 3D peaks that represent specific frequencies present at a given millisecond. These 3D peaks are flattened into a 2D spectrogram, creating a heat map that maps frequency intensity over time. We then apply MEL filters to this spectrogram. This process extracts MEL frequency substral coefficients, or MFCCs, which align the frequency data with the logarithmic scale of human auditory perception. Simultaneously, a voice activity detection algorithm identifies and removes segments of silence, preventing the pipeline from processing empty noise. Machine learning depends on this initial step, the mathematical reduction of the physical world into discrete, quantifiable features. This requirement for discrete representation applies to text as well, though the input begins as a string of characters rather than a continuous waveform. Attempting to map entire words as unique semantic units results in vocabulary bloat. The model would need a distinct identifier for every possible word, tense, and misspelling. Byte Pair Encoding, or BPE, solves this by breaking words into subword units. These are determined by frequency clusters rather than linguistic rules. Variants, like WordPiece, ensure that even unknown words can be constructed from these existing subword vector ID codes stored in a centralized vocabulary library. Whether the input is a waveform or a text string, the extraction layer's function is to decompose human context into unified mathematical representations. Once features are standardized, they are ingested into the architectural engine. In streaming ASR, data arrives continuously without a defined endpoint. The system must process and transcribe audio in real time as the signal is received. This is handled by the RNN-T architecture. It uses a transcription network that updates continuously, outputting character probabilities as individual data frames arrive. This sequential constraint is removed in offline processing. Transformer architectures allow for parallel processing, where the entire input sequence is analyzed simultaneously across an attention matrix. Both systems utilize an encoder-decoder dynamic. The encoder transforms the input features into an internal representation, which the decoder then uses to generate the final output. The choice of sequence model defines the deployment capability, balancing the parallel accuracy of a transformer against the sequential, real-time response of a transducer. Modern models go beyond sequence mapping to develop a generalized understanding of the data environment. This is achieved through self-supervised learning, where the model identifies patterns within unlabeled data by using the data's own structure as a training signal. The Joint Embedding Predictive Architecture, or JEPA, demonstrates this. Instead of predicting missing pixels or audio, the network predicts an abstract feature vector within an embedding space. Predicting representations is more efficient than generating raw data. The model focuses on the semantic components of the input that align with the true representation in the latent space. Foundation models leverage this to learn the underlying structure of the data rather than memorizing surface patterns. During the optimization phase, the architecture must correct its errors to align its predictions with reality. In speech systems, we face an alignment problem, mapping a long sequence of audio frames to a much shorter sequence of text. Connectionist Temporal Classification, or CTC, provides an alignment strategy. It uses a matrix to map audio frames to text, inserting blank tokens to account for timing variations. CTC calculates the sum of probabilities for all possible alignment paths. This produces a single loss score that represents how closely the model's output matches the target text. Gradient descent uses this mathematical score to navigate the model's weight landscape, adjusting parameters to reduce the error. This process requires careful management of the gradients. We use regularization and tuning to prevent vanishing or exploding gradients from stalling the training process. Without the specific alignment constraints provided by CTC, the architecture will fail to map the relationship between the audio signal and the resulting text. To move from passive mapping to active decision-making, the system utilizes reinforcement learning. This is structured through a Markov decision process. The agent exists in a state, takes an action based on a policy, receives a reward, and transitions to a new state. The agent optimizes its behavior by updating a queue table, which stores the expected reward for every action taken in every possible state. When the state space becomes too large for a table, as in complex DAME environments, a neural network is used to approximate these values, a process known as deep reinforcement learning. The agent must continually balance the exploitation of known high-reward actions with the exploration of new actions that may improve the policy. Markov frameworks provide the mathematical structure for an agent to evaluate its environment, transforming the system from a passive predictor into a decision-maker. Theoretical optimization is the first half of the process. The second is binding the model to a production environment. This graph plots the fixed trade-off between inference latency and model accuracy. In a production container, increasing accuracy typically requires more parameters or compute time, pushing the system toward the threshold of real-time usability. Retrieval-Augmented Generation, or RAG, provides a method to update the model's context without retraining. A query triggers a search of an external database, and the results are integrated into the prompt before inference. At scale, this requires data pipelines and parallel vector stores capable of retrieving information across millions of entries with minimal latency. Once live, the system must be monitored for data drift, which occurs when real-world usage patterns diverge from the data used during training. The engineering task is complete only when the system maintains its performance metrics under the constraints of a live environment. From signal processing with STFT to representation learning with JEPA and deployment through RAG, these concepts form an integrated topography. They are the connected stages of a single engineering pipeline. Operating at this high level requires managing the seamless integration of these disparate layers into one unified system. This map serves as the syllabus for our upcoming series. We will be releasing 3 videos every week, providing a detailed technical breakdown of each node in this architecture. True understanding of these systems comes from analyzing these structural fundamentals. Subscribe and join us as we begin the first breakdown.